Hey everybody, this is a 9-volt battery I found in the closet, and it's got two compartments like all batteries do. One compartment's designed to lose electrons and one's designed to gain electrons, and what powers it is an oxidation reduction reaction. And there's one way quick you can test if this is good. And you just do, let me try that again. Ooh, that's interesting. Okay, let's go talk about oxidation reduction reaction. Right now. Well, hi everybody. Hi, Mike here, and today we're going to talk about, my tongue is kind of numb. Today we're going to talk about oxidation reduction reactions. Unlike exchange reactions, you're going to find that the charges of things, or at least the charges they appear to have, which we call oxidation number, we'll get to that later, is going to change. And that's because unlike ions just changing what they're paired with, these things are going to actually transfer electrons. And so if you want to just remember what's going on here, all you got to remember, it seems quite sophomoric, but it works. Leo, the lion, goes grr. Leo stands for loss of electrons, is oxidation. Grr stands for gain of electrons, is reduction. And that's really the pushing force behind an oxidation reduction, or if you want to sound cool, call it redox reaction. And so here's the thing also to understand. You can't have one without the other. I can't have something losing electrons without something else gaining them. And so you notice when you have a battery that you have two poles on it called anode and the cathode, and that's because one side is losing and one side's gaining. And if you want to really be interested in that, we'll let you discover that in Gen Chem 2. But let's do an example of a redox reaction, and we'll go and write all three forms of it next. All right, so here is, and by the way, it doesn't have to be a lion. Leo can be a friendly dog that's just playful. But it needs to go grr, whatever Leo is. So, okay, let's go ahead, and this looks intimidating, like you can't tell, hey, what's changing here and what's not? So let's bust it up, everything that's an electrolyte, into its respective ions. Now, you might remember that in NO3, and you have a solubility chart if you need to sort of cheat on it, but NO3s are -1s, which means that that tin has to be a 2+. And it is in solution, of course this is the ionic form, it's really in there, with 2 nitrates. Fair enough? And then I could see that this silver is a +1. And that's because it's combined with 1 nitrate. And then that silver on the right is silver metal. We don't change anything. We don't ionize anything. It's not an electrolyte, and so a solid is not an electrolyte. Now, tell me, what's the charge on that tin over there on the right? It's paired with 4 nitrates. It must be a +4. And with it are 4 NO3 minus. Now, we're going to find out in a hurry that we've got a bit of a problem. Because instead of balancing atoms, a lot of times you can balance polyatomic ions, and you might notice that there's 3 nitrates on the left and 4 on the right. And that's because what needs to happen here is we need to balance this thing with a coefficient. There needs to be a 2 right there. And therefore, there needs to be a 2 over there. And that would make a 2 there and a 2 there. And now we can go and proceed to the net ionic portion, or way to represent this equation is we will then net ionic cancel all the spectators, which I will just circle so you can see what they are. There's 2 nitrates here, and there's 2 nitrates here, and there's 4 nitrates there, and they're all going to cancel. And that's going to clean up things a lot, and that's going to help us see what's changing, which is the goal of finding out what's going on in a reaction, except in this case, things be changing their charges. And by the way, always, if you want to make sure that you're doing the right thing, the charge and the number of atoms on each side of the arrow have to be the same. Oops, look what I did. Almost didn't put a 2 right there. And so 2 Ag solid plus SN4 plus. Now, I'm going to show you something that is probably going to make this a bit easier for you. It's going to be a bit of culture shock at first, but it'll tell you what's oxidizing and what's reducing either. But I want you first to look at this, and can you see tin changed its charge? Silver changed its charge. By the way, when you have a metal, that you could just think of that being like a 0 right there. That's an element, and we'll talk about elements in a little bit. So now what I want you to do is, in your mind, take this reaction, because it's like, think of it like 2 equal arms of participating members, and split it into what we call half reactions. So this is a way to sort of help illustrate what's going on. So let's take the silver part and write it separately, and the tin part and write that separately. And then we're going to find out easier, it's going to be easier to find out what's going on. So we're going to say 2Ag plus goes to make 2Ag. I'll keep the 0 in there. You don't have to put the 0 in there, but it helps you see it. And then we've got SN2 plus and SN4 plus. We don't even have to put the S in there, but so now what you can do then with the half reactions is balance the charge with electrons. So charge, of course, plus 2 on the left for the silver. And let's see, remember, electrons are negative. -1. So the silver part, I've got a charge of +2 on the left, right? +2, 2 plus 1s. The charge is 0 on the right. And the way to make it the same would be to use 2 electrons on the left. Look at the tin down below, SN2 plus. Now they don't have to be 0, they just got to be the same. SN4 plus on the right. And so +2 plus 4, I could make both sides of the arrow +2 by putting 2 electrons on the right. And now it's really easy to see what's going on here. On the left, this is gain of electrons, because it's on the left, and it's on the left side and going into the equation, and coming out of the equation is Leo. So what we can say is we can say that Ag plus underwent reduction, or we say this is reduced. Ag plus was reduced. If something undergoes reduction, it was reduced. If something undergoes oxidation, it was oxidized. So tin 2 plus was oxidized. And anything can be oxidized or reduced. It's just that you have to see what the change is. What's losing electrons and what's gaining electrons. Now, if you don't like the electron thing, just remember you can say that oxidation is also increase of charge. So you see that an increase would be, of course, it going from +2 to +4. And reduced, it kind of sounds like reduction. Something is reduced. It's a decrease in charge. So if you don't like splitting it into half reactions and see what's got electrons going in and what's got electrons coming out, then you could do it that way. Now, this is not necessarily the scope of the course of Gen Chem 1, but I'm going to push you folks a little bit because I know you can handle it. If something is undergoing reduction, it is oxidizing, it's something else. So if something is undergoing oxidation, it's reducing something else. So first of all, you can't have a reduction without an oxidation. And second of all, the thing undergoing reduction is oxidizing something else. And so here we would call silver the oxidizing agent. Now I'll tell you right now, you'll see that term again in your life, oxidizing agent. And then the tin is the reducing, tin 2+. And that, in a nutshell, is almost everything you need to know about oxidation and reduction. And how could you tell if something's oxidized? How could you tell if something's an oxidation-reduction reaction and not a precipitation reaction or a acid-base reaction? Well, those other things don't have any charge change at all. Nothing ever changed its charge. If you go to an acid base, an H+ is an H+, and whether it's with water or not. And so you can spot coming easily an oxidation-reduction reaction because the charge changes. And so, now here's the thing, everything we did here was ionic, but molecular covalent things can undergo oxidation and reduction too. So how do we deal with that when there's no charges? Well, that's when we talk about oxidation number, coming up right now. Okay, so when something is not ionic, you have this sort of generic term called oxidation number. It could be an ion, but basically something that is an element, we say it's got an oxidation number of 0. So if you had like copper in the last example, that had a charge of 0, we said, but if you had something like N2, we'd say that's an element. And so each nitrogen, and by the way, you pay attention to oxidation number with atoms, individual atoms, not the whole compound, because it's the atoms that are losing or gaining electrons. And then we kind of went through this before. If you had an ion that was it would be the oxidation number would be the charge. So if I have an iodide, that'd be -1, and if I had a calcium, this would be a +2. So nothing here should be really all that foreign to you, but what about when it's in a compound? So what if I have something like CO2? Fair enough, I'm going to take CO2. The way you find out the oxidation number of everything is that you can lean on this. Almost a lot of important covalent compounds are going to be combined with hydrogen and oxygen anyway. And so here we've got a carbon, and we've got it combined with 2 oxygens. And this probably looks familiar to you. Oxygen is usually a charge of -2, except in CO2 there's no charges. This is covalent. This is electron sharing. So it's a little bit different, but you kind of treat it the same way. You'd say, okay, well, the rules, this is, rules or patterns, is that oxygen is a -2, and so that's -2, but there's 2 of them, and that would be a -4. So that carbon is a +4. It even gets kind of weird sometimes. Like, what if I had a carbonate? And you'll get to practice this a lot. That would be a 3 times a negative 2 equals minus 6. And so how is that going to exist in such a way that it's minus 2? The only way that whole thing can have a charge of minus 2 is if that carbon was a plus 4. And so you see, even things that are not metallic, we think of them as like having an oxidation number, even though they're not, like an ion, because that's all electron sharing and everything except those ions I just showed. So now if you had something kind of like this, carbon monoxide plus O2 goes to make CO2. And we want to say, hey, what's being oxidized and what's being reduced? Well, first of all, I need to do a quick balancing act here, because that's got 3 oxygens on the, right? 4 oxygens on each side, so I'd have to do that. But then again, these coefficients here, 2 and 1, they don't have anything to do with the oxidation number at all. What I got to do is just lean on those rules, and I'd say, hey, there's oxygen. I'll do the easy one first. That's 0. And then here is a carbon. Well, we already did CO2. That would be, oxygen here would be minus 2. And there's 2 of them. And that carbon would be then a plus 4, as we spoke about earlier. And so what about carbon monoxide? That would be a minus 2 for the oxygen. That's the rules. But that carbon, to be combined in a 1-to-1 ratio, would have to be a plus 2. So if we keep track of what's going on here, carbon went from plus 2 to plus 4. Oxygen went from 0 on the left to minus 2 because it was combined with carbon. So carbon increased its charge and it's actually not charge, increased its oxidation number, and so that would be oxidation. I always tend to remember reduction's the other one that's going down. And so oxygen went from 0 to minus 2. That's going down, even though it crossed 0 and went down negative. That's reduction. Hey, and guess where oxidation got its name from? If you put oxygens on a bunch of stuff, you are oxidizing it, because oxygens are minus 2. It's going to increase its charge. So if you take iron, for example, iron will undergo rust. Rusting. And then plus, going to make Fe2O3. I'll do a 3/2 O2 here. That's oxidation, folks. That's a 0. And that iron, can you tell what it is? Try to figure out what that charge is on the iron. I know that the oxygen is a 0 because it's an element. That's -2 times 3 is minus 6. And so the irons have to be plus 6, but there's 2 of them, each having a charge of plus 3. Now you didn't have to know it was exactly plus 3, but you see that it went from 0 to plus 3, that's oxidation. And that 0 to minus 2 was reduction. And so if you ever have 2 oxidations or 2 reductions, you did something wrong, because the universe didn't do it. That's not what can happen. And so that is a quick treatment of what is oxidation and what is reduction. And now you can go and do something ionic, break it into its net ionic equation. So if you have something with ions like that example with tin and silver, break it into its ionic form, and the charges pop out at you. If it's something that is a compound combined with oxygen or hydrogen, you might have to go dig into what the other thing paired with oxygen or hydrogen is. And so practice, but something's changing its oxidation number, or it ain't a redox reaction. Folks, this has been a good talk. Nice chat. Take care, and we'll see you next time. Bye.